So this is ELC131 Circuit Analysis 1, and in this presentation we're going to talk about capacitors in AC circuits. Now, when we apply a sinusoidal AC source to a capacitor, during the positive half cycle, as shown in Figure 1, the source voltage is positive to negative, and current will flow to charge the capacitor as shown. And the charge, of course, will build up on the plates of the capacitor as shown, positive on the top and negative on the bottom. During the negative half cycle, the polarity of the voltage source changes to negative to positive as shown, and current will flow in the opposite direction to charge the capacitor as shown, with negative on the top plate and positive on the bottom plate. So with an alternating current source applied to the capacitor, current will flow all the time to charge the capacitor, either positive to negative or negative to positive as shown. Now, the equation given shows the current that flows to charge the capacitor, IC equals C times dV dt. Now, Figure 3 shows us one cycle of an AC signal, and of course we'll describe this or define this as being a low frequency. And with a low frequency AC signal, the voltage changes slowly. Therefore, the current is smaller, and of course, if the current is smaller, the opposition to current is larger. Figure 4 shows us 3 cycles of an AC signal, and we'll describe this as being a higher frequency. And of course, with a higher frequency, the voltage changes faster, therefore the current will be larger, and the opposition to current will be smaller. Reactance, symbolized by the letter X, measured in ohms. The unit symbol is the Greek letter omega. And reactance is the frequency-dependent opposition to a sinusoidal alternating current. Capacitive reactance is the reactance of a capacitor. This is pronounced X sub C. Mathematically, X sub C equals 1 over 2 pi Fc. To show an example calculation, the reactance of a 100 microfarad capacitor at a frequency of 1 kHz is 1.59 ohms. Now, the equation again that describes the instantaneous current to charge a capacitor equals C times dV dt. And if we look at the voltage sine waves shown in Figure 5, at 0 degrees, dV dt is a large positive value. Again, dV dt is merely the slope of that sine curve at 0 degrees. And this sine curve will have a large positive value at 0 degrees as sketched. At 90 degrees, dV dt is 0. At exactly 90 degrees, the slope of this function is 0. In other words, voltage does not change as time changes at exactly 90 degrees. At 180 degrees, the rate of change of voltage is large in the negative direction. And at 270 degrees, again, the slope of this sine function is 0 at 270 degrees. And of course, at 360 degrees, we're back at the beginning, and the slope is a large positive value. So if at 90 degrees dV dt is a large positive value, then IC will be a large positive value as shown on the graph of figure 6. At 90 degrees, since dV dt is 0, IC will be 0 as shown in figure 6. At 180 degrees, dV dt is a large negative value, so IC will be a large negative value. And at 270 degrees, since dV dt is 0, IC will be 0. And again at 360 degrees, we're back at the beginning. So we can see from figure 6 that the capacitor current leads voltage by 90 degrees. To help us remember this, we'll remember the mnemonic or memory aid that says ICE. Again, in the old days, source voltage was represented with the capital letter E, so the memory aid was I comes before E, current comes before voltage in a capacitor. Now it's difficult to sketch these sine waves to represent the phase difference between current and voltage in a capacitor. So we'll illustrate this using a vector diagram. And figure 7 shows us the vector diagram that illustrates or represents the phase difference between the current and voltage in a capacitor. Now we're going to place the voltage at the reference point, the positive x-axis, since in the plot of figure 6, voltage started at 0 degrees. And the capacitor current is 90 degrees ahead of voltage on this vector diagram. So again, figure 7 provides us a way of illustrating this phase difference of voltage and current in a capacitor by using a vector diagram. Again, when applying an alternating current to a capacitor, current is flowing all the time. Current flows to charge the capacitor, positive to negative. Current flows to charge the capacitor, negative to positive. The higher the frequency, the faster that the capacitor charges. Therefore, the higher or greater the current that flows to charge the capacitor is. So we find that the opposition to current in a capacitor decreases as the rate of change increases or as the frequency increases. Capacitive reactance is the opposition to sinusoidal current provided by a capacitor, and mathematically x sub c equals 1 over 2 pi fc. And in a capacitor, there's a time difference, a phase difference, between the current that flows to charge a capacitor and the voltage that charges a capacitor, or the voltage applied to a capacitor, and that is that the current leads the voltage by 90